All right, so now we're going to move on to a topic called the method of undetermined coefficients. So we've just got done talking about how to solve the homogeneous part of a linear equation, a linear differential equation with constant coefficients. Now we're going to consider the case where the right-hand side of our equation isn't just zero, but it's some function. This is one of a few methods that we're going to discuss. And since there are multiple methods, there's a reason to have multiple methods. This method has strengths and weaknesses just like any other method, and sometimes one method may be better to use than another. The advantage of this method is it's actually relatively easy, but it does involve a lot of algebra and a lot of just calculus and solving of equations and things like that. So let's just go back and think about our general problem. We have a linear differential equation where L is some linear differential operator describing some expression involving y and some of its derivatives. And phi of x is some function that we're given, and we want to find what's the function y. So what have we done last week, is we realized that we have to find two parts to this problem. We have to first solve the homogeneous equation, and that solution we're calling y sub h. It is a general solution, and it has unknown constants or coefficients in it that we're going to use, will help us ensure that our solution satisfies any initial conditions that we're given. Now what we're going to do is decide how we find the other part of our solution, the particular solution to our original equation. So this is just going to be one specific function, y sub p, that will solve our equation, but it may not satisfy some initial conditions, and we have to add to it y sub h to create a function which not only solves our equation L of y equals phi of x, but also has some unknown constants which we can plug in our initial conditions to figure out what they are. Again, if our equation is of order n, then y sub h contains n unknown constants, which we can determine by solving a system of equations once we're given those n initial or boundary conditions. So here's the general idea, the method. Well, basically what we're going to do is we're going to make an educated guess at what this y sub p is. And again, this makes the method actually somewhat not too difficult, but you have to get used to understanding how we make this educated guess. So this guess basically is going to take on some general form with some unknown constants or undetermined coefficients. That's where this method gets its name. And that general form is going to be interpreted by us by looking at the function phi of x that we're given on the right side of our equation. So in general, if we have a polynomial over there, or an exponential function, or some trig functions, we should basically guess something like those. Because when you differentiate polynomials, you get polynomials. When you differentiate sines and cosines, you get sines and cosines. When you differentiate exponentials, you get exponentials. So that's the general idea behind our guess. Once we have our guess, we basically plug it into our equation and do the calculus. We compute all the derivatives we need to, we combine everything algebraically, and we set that expression equal to our given phi of x. And then we make observations about what those undetermined coefficients must be equal to in order to make that equation true. So in this video, we're going to go through one of these cases, what I call the basic cases. There's three basic cases. Then after that, things can get arbitrarily more complicated, but you can basically get everything from understanding the basic cases. So let's consider the polynomial case. So what do we have? We have a second order linear equation, and our phi of x is a second degree polynomial. So here's the idea. What kind of function would y have to be so that if we add it to its second derivative, the result is going to be a second degree polynomial? So again, what must y be in order to make this happen? Well, let's just think about it. Y is going to have to be a polynomial, because if I have y as a polynomial, its second derivative is a polynomial, and when you add polynomials and regroup terms, you have a polynomial. So it has to be a polynomial, but also it basically has to be a second degree polynomial. Let's think about that. If y is a second degree polynomial, its second derivative is a constant. So a second degree polynomial plus a constant is a second degree polynomial, and that's what we have. So our guess should be, guess that y is a second degree polynomial. But I mean, second degree polynomials have a general form. There's some coefficient times the x squared term, plus some coefficient times the x term, plus some constant term. So those three things are our undetermined coefficients that we're going to use. So our guess is that y should be a second degree polynomial. And this is how we make our guess. Again, the letters I'm using here, A, B, and C, can be anything you want. Just call them whatever you want. But in this case, I'm just using A, B, and C. So our particular solution should be of this form. So let's go ahead and compute its second derivative and then plug it into the equation. So the second derivative of this is just going to be 2a, because the constant term, c, after one derivative is 0. The b times x term after two derivatives is 0. And the ax squared term after two derivatives is just 2 times a. So that's what this 2a is here. And to add to that, we're going to add y, which is what we have here. Now just simplify what that is. What I mean by simplify in this case is regroup terms. You want to have an x squared term, an x term, and a constant term. And then we're going to set it equal to our given phi of x. And then all we have to do to make them equal is to make the coefficients match. So in this case, since ax squared is on one side and x squared is on the other, the only way those two terms can be equal is if a is 1. I have a bx term, and I have a negative 2x term. So b must be negative 2. Now for the constant term, I have c plus 2a equals 1. Well, we've already determined that a is 1. So c plus 2 equals 1, and that tells us that c is negative 1. So that's how you go about determining the coefficients. You just match the different power functions on each side of the equation and just say that they each have to have the same coefficient. So our particular solution is just the function x squared minus 2x minus 1. And again, if you want to go back and double check, take this specific function, plug it back in, and you'll see that it works out. But the whole point is, by choosing it to have this form, it was an educated guess because of what we know derivatives of polynomials are polynomials. So we basically chose it, and then we forced it to be the solution by setting it equal to that function on the right after we plug it into the L of y, in this case y double prime plus y, and then just made them equal, made it work. So in general, if the function on the right-hand side is an nth degree polynomial, so like some x to the n term plus or minus some x to the n minus 1 term and so on, and we're just going to let our particular solution y sub p be of that form, where now each coefficient, a sub n minus 1, and so on, down to the constant term a sub 0, those are the undetermined coefficients. And you plug it into your equation and regroup the like terms, so you have a polynomial in a form of some constant times the x to the n term and so on, and you set that equal to phi of x, and then you just match the power functions. So the x cubed term on both sides, those coefficients have to be set equal to each other. So since there's n plus 1 of these numbers, a0, a1 up to an, we have a system of equations of n plus 1 equations and n plus 1 unknowns. So now, let's do an entire problem. So this is the first time we're solving really an entire second order or higher order problem, initial value problem, that's not a homogeneous equation. So we have our second order linear operator, L of y, described here, our function phi of x described here, and we have our two initial conditions because this is a second order equation. So there's 3 steps. First, find the homogeneous solution. L of y equals 0. So we look at our characteristic equation, or characteristic polynomial. It's going to be r squared plus 2r plus 1. That factors as r plus 1 times r plus 1. So our characteristic equation has a solution, has one solution that's repeated, and it's r equals -1. So we know from this past week that how to construct our solution to the homogeneous equation. Since it's a repeated root, we construct y sub h in this manner. We have an e to the minus x term plus an x times e to the minus x term. And c1 and c2 are the constants because they could be any constants we want. And those are the constants that we're going to have to determine from the initial conditions. However, we can't do that yet. We have to construct our entire function y before we plug it into the initial conditions. So that's why we have to now go and determine our particular solution, y sub p. So again, there's our problem. Phi of x is a first-degree polynomial, or a linear function, same thing. So we define y sub p to be a linear function with 2 undetermined coefficients, a1 and a0. If we plug y sub p into our differential operator L of y, the second derivative is 0. The first derivative is a sub 1, but we have a 2 times the first derivative, so we have 2a sub 1. And then to that we add y, which is a sub 1 times x plus a0. So regrouping those terms, we have a1 times x, and then we have a constant term, which involves 2 of the terms that we had to add together, 2a1 plus a0. And we set that equal to our phi of x, or 4x minus 2. So the x term tells us that a1 has to be 4, and if a1 is 4, then what we have here is 8. So what we really have is a0 equals -10. So our particular solution is now 4x minus 10. And we added to that the homogeneous solution, which we got previously. And this entire expression now defines our general solution. It's the general solution because we haven't plugged in the initial conditions yet. There are 2 constants here, which we haven't figured out what they are. So now we can do that. So there's our problem. We found our solution in 2 steps, found the homogeneous part and the particular part. Now we have to differentiate because our second initial condition involves the first derivative of y. Again, notice we had to use the product rule for the second term, the x e to the minus x term. Now we use the first initial condition, y0 equals 1. That tells us that y equals 1. And then we plug in 0 for x into the formula for y. We just get c1 minus 10. Solving that for c1, we get c1 equals 11. Now the second equation, or second initial condition I should say, the first derivative at 0 is 0. So the first derivative is 0. And now we plug in 0 into our first derivative formula. We notice that there's 2 terms that are going to, well, there's a term that's going to vanish. This x e to the minus x term is going to vanish. And we already know what c1 is. It's 11. So by putting those things in, it's easy to see that c2 is 7. So there is our exact solution to this initial value problem.